who is an expert on acoustic and elastic metamaterials, especially cloaks. Davide has been a PhD student at Politecnico di Milano in the group of Professor Francesco Braghin, and he has submitted his PhD, will defend his PhD very soon, so he will be soon a more senior researcher. And so, Davide, please, it's your turn.
Hey, thank you, Sebastian, for this nice introduction. Actually, I'm very honored and thankful to all the organizers for this kind invitation. So thank you again, and let's dive in. The topic for me today is, as said, acoustic concealment, scattering reduction. And so, I mean, I will start by, see if I can, okay. I will start by reviewing some topics from the acoustic transformation theory, because it's just the tool that unlocked the past decade the possibility to achieve perfect cloaking. So the idea is just to write a mapping between the points of your cloak and a so-called virtual domain, which is filled by the background fluid, except by a very small boundary, ideally a point to which the inner of the cloak is mapped. In this way, when you consider the acoustic wave equation on the virtual domain, what you obtain is free field propagation, basically. And if you apply the mapping to this equation, you get the well-known transformed equation that simply kind of, when solved, represents the free field propagation, but just stretched and glued on the points of the cloak according to the transformation. And the last step is just to realize that this equation is formally equivalent to the equation of a special solid, the so-called pentamode material, that can support only a single state of stress connected to a state of strain, which is indicated here by this tensor S. And possibly it also has some anisotropic inertia, which is here indicated by this tensor rho. So basically, by comparing these two equations, what you can get is the specifications of your material properties to perform the cloak. And they kind of depend on several ingredients. The first one, as you can see, is the background material properties, but also you have these two tensors that define your material properties. The first one is V, the so-called left stretch tensor, which kind of represents the metric change, the local metric change induced by the transformation. So it just depends on how you write the mapping. And when you know the map, basically, you can compute the so-called deformation gradient or tangent map that represents how a spherical neighborhood of a point in the virtual domain is transformed by the transformation. And it can be further split into a rotation, R, a rigid rotation, whose effect is here represented by the rotation of the red arrows, and a subsequent stretch, which is what we're interested in, is the tensor V, which is symmetric and positive definite. So in the reference frame of its principal directions, you can represent it with its eigenvalues that just represents how the length are transformed. I mean, they represent the ratio between the actual length of the axis of this ellipsoid and the original length they had in the virtual domain. And the second ingredient that you need is this tensor P, which is a symmetric divergence-free tensor. You can choose arbitrarily. And upon the choice of this P, you can get different type of materials. For example, it's well known that if you use P equal to the identity, then what happens is that your material just supports the isotropic pressure, and you get kind of a standard fluid, except but it has an isotropic density. And this is the strategy they used, for example, at MIT, the group of Nicolas Fang, to implement this cloak. All in all, you can also aim for cloaks that have a scalar density. And this is the case of so-called pure pentamode materials. In this case, you should be able to write a map rotation-free, basically. So the rotation tensor is the identity, and in that case, you can use a P tensor to be proportional to the V1, and you attain the scalar density. and the anisotropy is all in the elasticity tensor. And this is another strategy that was implemented, for example, by the group at Beijing Institute of Technology to realize this cloak. All in all, what it means from the physical point of view is that to realize the perfect cloaking, you need an inhomogeneous material distribution. And this is because we want to bend rays basically with refraction, but also you need anisotropy. And this refers basically to the way in which you anisotropically stretch space. The information is encoded in that important tensor V I showed you. And indeed, if you compute the speed of propagation in one single point of the cloak along the principal directions N1, N2, and N3 of V, it turns out that the principal stretches are kind of refraction indexes that are scale factors for your speed. And this makes sense because the velocity in a given direction is just the background free direction scaled by the stretch. So if you compress space, you have to go slower, basically. If you have a dilatation of space, you have to go faster, basically. And the duality of material property comes out because in the end, what you aim at is kind of the speed of propagation distribution, and as the same distribution of speed can be implemented with different combinations of stiffness and density. So all in all, this is a very beautiful approach, but it also has some, let's say, drawbacks. And the major one is the fact that you are highly reliant on the fact that you can write the mapping. And this can be easy only usually for simple shapes. For example, these cylindrical cloaks, or in 3D, the spherical cloaks. But in general, it's not easy to write a map for a whatever shape. Let me put it like this. And also, if you desire to build a cloak that is only solid, so which does not require a working fluid, what happens is that you need to write not only a map, but a map that is rotation free, which of course increases even more the complexity of this task. So when I kind of started working on this, our question was, can we find a way to target a different shape than the usual cylindrical and spherical one, for which for sure the literature is restricted. And of course, we approached this, with engineering point of view. So the idea is maybe we are willing to accept some reduction of performances. So maybe we do not target perfect cloaking, but scattering a reduction, as long as it can be implemented easily and as long as it can be useful for practical applications. So first we wanted to kind of extend the usual approach for cylindrical cloaks to obstacle with an elliptical shape. And in doing that, we wanted to find ways to easily write a mapping that can lead to solid cloaks, so pure pentamode cloaks. And to do that, we naturally, came up to the idea of using the elliptic coordinates, for using which you can describe the inner and the outer of the cloak as coordinate lines, basically. Indeed, if you look here, this is a representation of the virtual domain. We use a pair of coordinates big R and big theta to describe the points here. And if you keep fixed R and increase this angle theta, you kind of go around an ellipse, which is your coordinate line. In the same way, if you keep fixed theta and increase this R, you go along this hyperbola. And a single point described by these two coordinates is mapped into a single point on the cloak, which is described by another set of coordinates, small r and small theta. And the mapping, we defined it in this way, in which you see we keep fixed the let's say, tangential coordinate, the angle, and we kind of just map the inner of the boundary to a smaller boundary, as it is usually done in polar coordinates, basically. And you see it here with the inverse map, that kind of the big R is obtained as a function of the small r, which is called f. So the aim is to obtain a scattering reduction, because the cloak then will perform like an obstacle size like this. Okay, so once you have this map, what you can do is you do your math. Besides the computation, what is important is, as I said, the stretch tensor, the left stretch tensor, and to realize which are the principal directions of anisotropy and the associated refractive index, basically the associated stretches. And it turns out that these principal directions are everywhere aligned with the base vectors of this system. So they are kind of aligned tangentially to coordinate lines. So we have our anisotropy, which is kind of defined to be either radial or tangential. I use these names, although it's not polar coordinates, just to give you an intuitive idea. So this is pretty much similar to what happens in polar coordinates, but it turns out it has some differences actually. The first one is that, strictly speaking, the rotation is not zero everywhere. So you have a rotation tensor, which is not the identity. And so besides computation, let's look at this picture where I can show you from where the rotation comes. The idea is, if you look, for example, at the point on the inner boundary of the virtual domain, this is mapped into a point on the inner boundary of the cloak. And in particular, if you consider the spherical neighborhood we have seen before, it is kind of translated here, but not with the same orientation. And the orientation, if you do the math, you realize that this orientation follows the tangent to the coordinate lines. And so the rotation you get comes from the fact that the coordinate lines are hyperbolas that bend around the foci. All in all, on contrast, you can also realize that since the hyperbolas tend to straight lines far from the foci, there will be a lot of points inside the virtual domain that are mapped into the cloak with almost the same orientation. And so the rotation is bounded to low values for a lot of points, and just the points close to the boundary have a rotation. And by appropriate choosing of the map, you can limit it. And I will show you. And if this rotation is then limited everywhere, we can kind of pretend it is not there and use the material specification for a pure pentamode. And we will see that even with this neglecting of the rotation, it can still perform good. So the other big difference with respect, this rotation does not happen in polar cloaking, because in that case, the coordinate lines are just straight line emanating from the origin. And so it's easy to see that a similar map in polar cloaking does not produce any rotation. Then the other big difference with the usual polar cloak is that even if the rotation will be strictly zero everywhere, you can kind of not obtain perfect cloaking for all the possible incidence directions. And this is because even the smaller bound, you can make this inner boundary of the virtual domain the smallest as you want, but it never shrinks to a point. In the limit, it just shrinks to a line joining the two foci of the coordinate system. And so you will have more favorable directions. For example, the most favorable direction is incidence from above, and the worst favorable direction is incidence from the side. But still, as I said, if with this approach we can get a systematic way to design cloaks that are easy to implement, we are okay even with a non-perfect cloak and with some scattering reduction that is of industrial relevance. Let me put it like this. So if you pretend it's pure pentamode cloak and you do the math, you realize that the elasticity tensor written in the system of principal direction of anisotropy, so radial and tangential stiffness is basically we're looking for, because of the equal scaling factor of the elliptical coordinates, it turns out to simply depend on the first derivative of the function that maps the small r coordinate into the big one. And so this, of course, gives you the freedom of designing the map F upon requirements on the elasticity tensor. And it's pretty easy since the relationship between the elements of the elasticity tensor and this function is so easy, I mean, it's pretty easy to design a map that for your purposes. For example, if you use a simple linear map, what happens is that the first derivative is constant in space. So if I'm mapping linearly the big R coordinate onto the small r1, so you get this deformation of the rays, and it turns out that your radial and tangential stiffness, basically the elements of the elasticity tensor along these directions, are of course different, but they are equal. I mean, they are constant in space. And this can result in ease of implementation from the point of view of the microstructure, because the inhomogeneity is only demanded on density. Then, since you have the analytical formulas, you can also compute the local rotation inside the cloak. And as I told you, there are a lot of points for which the rotation is really close to zero, and the maximum of rotation is just felt usually in the inner of the cloak, where you have the maximum of rotation when displacing the points from near the function. And of course, as I said, you have the analytical formulas. So what you can do is even to build these maps that represents the maximum rotation in the cloak and the average rotation in the cloak upon choices of the geometrical parameters of your problem. For example, here you see the ratio between the major and minor axis of the obstacle. And also you see here on this axis, you have the geometrical reduction of the vertical axis, when you consider the obstacle and the equivalent obstacle, let's say the inner boundary of the virtual domain. And so you see that I mean, the most of the combination, you can assess that the mean rotation stays bounded to low values. And even here you can check whether the configuration you are targeting, you have, which is the entity of the maximum rotation. But also this approach gives you the freedom, as I said, to select other maps. So in this case, for example, we aim at reducing as possible the rotation, as you can see here. And this is done by selecting a mapping that displaces the minimum possible, the points on the inner, the points that are close to the focus from the original position. So they are kind of mapped the closer possible to the inner boundary of the cloak. And this, of course, gives you smaller mean and the maximum rotations. And of course, is paid in terms of the complexity of the material properties you have to implement. So you have kind of these tools that can allow you choose upon a trade-off on how big is your rotation. So how big would be your approximation in building a pentamode cloak, and how hard you are willing to accept when you face the stage of designing the microstructure. So as said, we are kind of pretending rotation is not there, and we can even assess if this approximation leads to interesting results, or neglecting this rotation leads to complete spoiling of the performances. In this case, you see we purposely designed a cloak with a very high rotation, at least the maximum, and so the mean, and checked comparing the uncloaked scenario with the cloaked one, and with the, let's say, expected scenario, which is basically the scattering of the inner boundary of the virtual domain. And you see here we're assessing 3 directions of incidence from above, 45 and horizontal, and comparing the uncloaked and cloaked scenario. You can see here visually that the scattering and the shadows are reduced, and the cloak performs close to what expected, even if you have a big rotation. We can also perform these numerical simulations as a function of the incident wavelength. So you have frequency increasing here for vertical incidence 45 and horizontal, and we can pick up the scattered pressure from the and normalize it with respect to the scattered pressure in the uncloaked scenario. So below 1 is good, basically. and compare in blue the cloak and in black the expected behavior you would expect if you do not neglect rotation. And you see that even they are not equal, obviously, because we are not considering the rotation, they are kind of close. And so, I mean, even with this high rotation, you can be safe in using this approach to build solid cloaks, pure pentamode cloaks. So the next stage for us was to try to find an experimental validation of this. And to do that, we chose the linear map, the first one I showed you, because in that case, as I told you, you have homogeneous elastic tensor, and you split the requirement of having inhomogeneity and anisotropy, one onto density, which takes all the inhomogeneity, and one on the elastic tensor, which takes all the anisotropy. And this results in a great advantage when you want to design the microstructure, primarily because we are dealing with a non-axisymmetrical problem. I mean, if you consider the way in which usually the inhomogeneity is implemented, you kind of discretize the distribution of the inhomogeneous distribution, and then inside each block, you substitute a single microstructure, basically. So if the problem is axisymmetric, kind of the usual circular cloak, everything repeats equal in the tangential direction. And so you just need to optimize few cells in the radial direction and repeat them. But then if you analyze a problem like this, in principle, you should optimize all the unit cells in a quarter of the cloak. And if you use this map, for which the elastic tensor is constant everywhere, then it's faster to do that, because we know in literature there are known geometries to implement pentamodes with independent control on elastic properties and mass and density. So for example, we used this, which is inspired by the work that they did in Beijing Institute of Technology. And since you have the constant elastic tensor everywhere, what you can do is you can design this hexagonal frame, basically, once and for all, to implement the anisotropy in elasticity you need, and then repeat almost equal to itself everywhere in the cloak, except by you change the size of these masses that change locally the density. And this results in great advantage when you have to perform the numerical optimization of the structure. All in all, it also has some drawbacks, because you see, having demanded all the inhomogeneity on the density, it turns out that the better the cloak, the better the performance you want, the biggest is the difference between the maximum and minimum density you have to achieve. And since we wanted to produce an experimental specimen with one single material in one single piece, we have kind of a bound on the maximum difference between maximum and minimum density, which is set by the fact that the overall density here, homogenized, just depends on the filling fraction of aluminum, which is the material we choose. So if you look at this graph, in which you have the ratio between maximum and minimum density in the cloak upon choices, for example, the thickness of the cloak and the equivalent reduction, so of a geometrical size, so the vertical axis of the obstacle over the vertical axis of the equivalent obstacle in the virtual domain. You see the better you want it to perform, so the biggest the reduction, the geometrical reduction, the bigger, as I said, it is this difference, but we have a bound. And so for this reason, since we were able just to produce a cloak in one piece in aluminum, we just aimed at producing a scattering reduction of almost 50%, which of course is not perfect cloaking, but can be of interest in applications and to validate this idea. So, when you know your targets, as said, you can discretize the distribution and optimize all the unit cells. You end up with a bunch of unit cells that can be piled according to their location in the cloak in something like this. In this picture, they are all equal because just of ease of drawing, but you have to imagine all of them are different. and then you want to deform them around the cloak because they have to be aligned to the principal directions of anisotropy. And since we are using an analytical method, we know the analytical formulas for these directions. And so it is pretty easy to do this stage exactly with a conformal mapping that takes our cells and displaces them, not changing in principle the optimality of their design you have just performed. And once you do that, you get to something like this, which is the fabricated specimen. And before doing the experiments, we just wanted to assess numerically its performance. So what we did is we took the microstructure, as you can see it, and send a plane wave in a numerical simulation against it, collect the scattered pressure field, the power of the pressure field scattered, and normalize it over the uncloaked power scattered. And compare the results to the expected behavior, which is this black line, which is plotted against frequency here. You see on the horizontal axis, it is expressed in terms of the wave number of the incident wave multiplied by the characteristic size of the microstructure. So increasing frequency, you have the expected behavior, as said, is approximately 50% reduction in scattered power. And this blue curve is the curve you get when you do the numerics without damping. And you see that when the wavelength is 3-4 times at least bigger than the unit cells, the long wavelength homogenization holds, and you get a behavior which is close to the expected, but is spoiled by the resonances, the shear resonances of this finite specimen. Of course, when you deal with ideal pentamode materials, they should not have shear resistance, but this is something you cannot achieve in reality. So you would have shear resonance anyway. But in reality, also you have viscous damping, a little bit of damping in aluminum. And if you include it into the numerical simulations, the resonances are kind of attenuated, and the behavior gets closer to that expected. At high frequency, the homogenization does not hold anymore, obviously, and so you do not get any cloaking effect. And also you see the scattering is bigger than the uncloaked scenario, just because the object plus the cloak is bigger than the object without, basically. In between, we have this transition region that it was very interesting for us, because it turns out that it coincides in terms of frequency, the frequency range in which we have a common single mode bandgap for all the unit cells. And this single mode bandgap means that in this frequency range, the cloak should work as a fluid, basically. So before doing this numerics, I would have expected this to be the best of the performance, actually. But what you see this peak, which is in contrast with this idea. And we are just trying to understand why this can happen. And our take on this is that since the specimen is finite in size, the idea is that at the interface between the fluid and the microstructure, the evanescent shear waves inside the single mode bandgap can take a role and maybe induce this scattering behavior. But that should be, we should need more investigations on that to get a proper explanation of this transition, probably. So once doing these numerics, what happens is that you are pretty confident that in the low frequency regime, it could work. And so we switched to the experimental validation. We put the specimen into a waveguide, as we learned from the work at PIT, to produce the 2D field you need. And then with the hydrophone, you can just pick up the field and reconstruct what happens inside the waveguide. But these are the experimental results. You can see this is the empty waveguide, so free field propagation. Then you have the uncloaked scenario, the cloak one, and what we expect if we consider the inner boundary of the virtual domain. And you have also two positionings, so incidents along the major axis of the ellipse and incidents along the minor axis. Okay, this will start again soon, but I hope you can see that then while we see again, that if you compare the uncloaked scenario and the cloaked one, what happens is you get a reduced backscattering. It can be seen, and also you can see that you have a less distorted wavefront past the obstacle. So you can see the cloaking effect also on the shadow. But we have some differences within what we expect, both in terms of the expectancy, the experimental expectancy when comparing to the boundary of the virtual domain, and both with the numerics. And this mainly relates to the fact that the intensity past the cloak is less than expected, and this much relates to absorption inside the cloak, inside the aluminum, and also the backscattering is a little bit better than what we expected. And this also may relate to the absorption, because even if scatters a little bit, the travel time inside the cloak can absorb. So I think of damping kind of a necessary evil in some ways, because you need it, because you do not have the shear resistance going to zero. So if you don't have a damping, the resonances will spoil your results, but also it prevents you to obtain, for example, a perfect shadows reconstructed past it, because it absorbs, basically. So all in all, this allowed us, this method allowed us to produce this experimental validation for a non-axisymmetric obstacle with more or less little effort in terms of optimizing the microstructure. But of course, you can see that in the bigger picture of finding a method to target, let's say, arbitrary shapes, this cannot be generalized a lot, because, I mean, you cannot find a whatever coordinate system for a whatever shape, and then you might be not that lucky to find the nice properties we have found for the elliptical system with the equal scaling factor and such a simple specification for elasticity. And so moving on, what I did with my colleagues Carlo and Sebastiano was to try to change the paradigm, the point of view, and kind of abandon for a little bit transformation acoustics and resort to optimization, basically. Optimization gives you the flexibility to address whatever shapes you want. Indeed, you see here the setting of the problem is just the obstacle that can be whatever, the cloak that can have a whatever shape. And then with this approach, we can also enforce a priori the kind of material properties we want to implement, basically. And then the algorithm will find the best performance given what you want, basically. And in this case, what we are using for the cloak is just the Helmholtz equation with inhomogeneous isotropic coefficients. So you see here we have a scalar density expressed as its reciprocal A and a scalar bulk modulus B. They just change in space. And this is because if you have isotropic material properties, obviously you do not have to care about all these direction of anisotropy and stuff like that, and it is much easier to implement. And then what we did to formulate the problem is just you set your material properties inside the cloak A and B to be dependent on two unknown fields that you use as controls, as degrees of freedom, U and V. We just use this exponential law because U and V can take positive and negative values, but A and B can be just positive. And then knowing this, you can find your unknown by minimizing a cost functional that basically tries to minimize the intensity of the scattered field in the ambient while keeping low the values of U and V. And this is because, you see, if U and V are 0, we just have the background properties inside the cloak. And for small positive U and V, we are just a little bit above, or negative, well, just a little bit below the background properties. So controlling the excursion of U and V just allows us to not to have material too much different from the background. And of course, this function, this minimization problem is constrained by a partial differential equation, which is the one that governs the scattered field. So it's just this same Helmholtz equation but rewritten in terms of the scattered field and with its own boundary conditions that are just the Robin boundary condition on the obstacle and Sommerfeld radiation at infinite. So to solve for this, what you do is you use standard techniques for constraint optimization. So you augment your functional with the constraint multiplied by an unknown adjoint function, and you take the first derivatives. I mean, the first variation of obligatory derivatives as you want. And if you do that with respect to the controls, you obtain this, that in strong form gives you a gradient of the function with respect to u and v. That depends on the scattered pressure and on the unknown adjoint function. And the adjoint function can be obtained if you take the first variation of the functional with respect to the scattered pressure. That gives you in strong form this PDE for lambda when knowing S. And this is interesting because this gives you the chance of setting an efficient steepest descent method to solve this problem. Basically, you start with a guess for your material properties. Using the Helmholtz equation, you find the associated scattered field. Using the found scattered field, you find lambda here, and then you have all the ingredient, scattered field and lambda, to find the gradient. And if the gradient is 0, then it's the optimal solution. If it is not, it gives you the idea of how to update your guess of material properties to get to the minimum. So this approach, as I said, is pretty straightforward and has been used by others. For example, by a group in Texas at Austin to design a cloak with uncertainty. On contrast, we wanted to stick to the deterministic problem and just use this formulation to integrate two phases of the design of a cloak. The first one, which is the definition of material properties, and the second one to define the microstructure that implements them. Usually these phases are pretty disconnected. I mean, you first find the material properties and then optimize the structure. What happens is that we wanted to marry them in one single phase in some way. And a first step towards this is to realize that your U and V controls are just not a whatever continuous function, but since you will then implement the isotropic material, for example, with hexagonal lattices of inclusions in water, then you can say that U and V are just piecewise constant functions, like constant multiplied by indicator functions. And in this way, you just take into account for the fact that your distribution is actually discretized, and you obtain the optimal solution already considering the discretization and not a suboptimal when optimizing a continuous distribution and then discretizing it. And of course, using this definition, you can update your definition of the gradient. And in the end, this means that we are just searching the 2n parameters and densities and bulk modules to fill these hexagonal cells that gives you no scattering outside the cloak. But I mean, having this formulation, what is interesting is that you can write explicitly the formula for the gradient. And what happens is that you are then very efficient in performing the optimization because you don't have to compute it numerically or to resort to evolutionary algorithms or stuff like that. And so here you see the solution you get in terms of bulk modulus and density and the performance when tested against the usual circular cloak before testing it on arbitrary shapes. And you see this, as I said, this approach has some advantages, gives you the flexibility of shape and simplified material properties, but also comes as everything with drawbacks. For example, as I said, we're using the Helmholtz equation, so we are just considering one single wavelength, basically. So if you put on the x-axis the incident wavelength and you probe your solution outside the wavelength you have designed at, which is indicated here with this blue dot, the scattered power will as soon as you move from that wavelength will increase. And so what you have to do to have a broadband working is to reformulate the problem, including in the cost functional more and more frequencies. For example, we have seen that including 3 frequencies in the optimization, you can get an approximately 30% width bandwidth around the target, basically. And same applies for the direction of incidence. Of course, if you consider only one direction, the blue one, I mean, you will have a very small scattering at that direction, but as soon as you move, then the cloaking performance are spoiled. And so you have to augment again your cost function, including the several directions. I also have some interesting data on the performance of the algorithm with respect to geometrical parameters. For example, here we are increasing the thickness of the cloak. As the thickness of the cloak increases, you increase the number of unit cells if you keep the size fixed, and this gives you more degrees of freedom. So if you look at the cost, the final cost, the scattered pressure field, we've increased the number of unit cells. You get to a low scattering. So the higher number of degrees of freedom, the better the performance is. But also, maybe this is sometimes kind of counterintuitive, the fastness of the optimization increases, because the higher the number of degrees of freedom, in this case, the easier the algorithm converges. You see the black axis, the red axis is number of iterations, and it decreases basically. So once done this analysis, we can apply it to arbitrary shapes. For example, this is a concave shape without and with the cloak, but also to pointy shapes. This is the uncloaked scenario from 2 direction of incidence, and this is the cloaked one. And you see that works basically. And as I said, our goal was to marry the 2 stages of material properties definitions and microstructure optimization. We have done our first step in discretizing the distribution, but we can go further and say, let me say that the isotropic material is implemented with this simple lattice of inclusions. And the simplest one is just the hollow cylinder, which is described by just 2 parameters, the inner and outer radii, such that we can build in a geometrical space, let me say, with the axis outer and inner diameter, all the geometrically feasible solutions. And the boundary of this is a closed curve that can be mapped onto a closed curve in the equivalent material properties space. So equivalent density and equivalent bulk modulus. And this closed curve tells you that whatever is inside is feasible, you can implement it, and whatever is outside, it is not with this simple unit cell. So you can use this boundary kind of inequality constraint for your problem to have your algorithm that finds only solution inside here, okay? And so with this simple geometry, we just realized that we cannot go below 1 with the normalized bulk modulus, so we cannot be softer, let's say, than water. So we also consider another unit cell, which is this endpoint at the start, with the folds that kind of allow us to maintain the symmetries required for isotropy. And then these folds make the unit cell softer, basically, such that when you map all the feasible unit cells in the geometrical space, here you have these 2 parameters, basically, and the boundary is mapped into the physical property domains in such a way that you can achieve bulk moduli below 1, basically. And so with using the 2 unit cells, you have this kind of big feasible region, and then you can start from the solution I showed you before, which is not constrained. You have a lot of dots that fall outside the feasible region. You can add the constraint to the optimization to find solutions that are actually implementable. And you see the performance are still good, and this gives you the chance to build, let's say, a microstructure with these hollow cylinders, either circular or star-shaped, and to perform a numerical analysis of what happens with the microstructure, which shows promising results. Also, In passing, I wanted also to show you that this PDE-constrained optimization is really flexible also with respect to the partial differential equation that governs your phenomenon. For example, this is a work we did. It was mainly done by Carlo Sinigaglia, which kind of targets thermal cloaking with active sources. So in this case, we aim at having the thermal field induced by the source unperturbed by the presence of an object with a fixed temperature. And so putting active source around, we can do the cloak, and I can show you that it works even with such complicated shapes, basically. So coming back to elasticity or acoustics, we can just say that the idea of an isotropic cloak can be very interesting in the context of elasticity. And this because it is known that when you apply the classical transformation theory to elasticity, you end up requiring very peculiar, let's say, material distribution properties like the Coursera material or the Willis constitutive equation. So if you are able for certain geometries to find a way that allows you to give good cloaking results, even if approximated with just isotropic materials, this can be of value, I mean, in terms of the implementability. And I mean, anisotropy in cloaking, as I told you initially, is much related to the fact that you are stretching space in an anisotropic way. And so if you want an isotropic material, what you can do is to use a map that stretches space isotropically. So, and this is the so-called conformal map. It is well known that if you apply a conformal map to the scalar wave equation in 2D, what you attain is that the scalar wave equation maps onto itself, basically. Just you have a non-constant speed of propagation, basically, and the refraction index is just the isotropic stretch you have induced by your conformal map. And so this can be used exactly to obtain exact cloaking, for example, for shear horizontal waves in elasticity that are governed by this scalar wave equation. If you use as a gradient of density, basically, it turns out that the gradient of density implements this distribution exactly. But it cannot be easily generalized to the in-plane problem. So P and SV waves that are in general governed by the full Navier equation. So while I was working with Momer Fedik and Richard Cluster, we came up to the idea of using the Helmholtz decomposition basically to the Navier equation, expressing the displacement as a function of two potentials, the scalar and vector potentials, which are then, they are governed actually by the scalar wave equation with a different wave speed. And so it turns out that if you simply map this equation for the potentials, it works as all other scalar wave equations. So what you need to do is just to implement a distribution of refraction index that scales both the P speed and the SV speed, basically. And if you do that, if you manage to find a material property distribution whose equations can be related to these equations, then what happens is that you get cloaking with the gauge transformation that corresponds to the transformation of the gradient, basically, for the displacement. Okay, it turns out actually that this is not actually possible exactly. And if you know a little bit of elastic cloaking, you know it from the beginning, because this gauge transformation is just the one that corresponds to the Coursera cloak. But I mean, as said, if we accept a little bit of approximation, we can just say that the equation governing the isotropic but inhomogeneous elastic materials is this one. If you assume to have inhomogeneity only in the density and you apply the Helmholtz decomposition, what happens is that you get two equations like this that rearrange gives you this one. And you can see that if the gradient of density is slow, and you can kind of neglect these two, what happens is that this equation is satisfied if the two parentheses are satisfied, and you get an equation for the two potentials, which is kind of the scalar wave equation with inhomogeneous material properties in density. And since the density appears both in the speed of P waves and shear waves, then you can use a distribution of density which varies in space in a slow manner to cloak both for SP, P, and SH wave at the same time, basically. And also this obviously works in carpet cloaking also for Rayleigh waves, which are kind of a combination of the in-plane mode. And okay, the idea is just with a slow variation of density, we can get the cloak working. All in all, the idea of having a smooth refraction index that bends wave is very sensible, and others have reached this point following other paths. But our let's say derivation allowed us also to quantify the amount of let's say approximation you are introducing, and it depends basically on your gradient of density, which depends on the map, on the material properties you are using, and on frequency. And so having this estimate, you can kind of a priori know that if your configuration would work, or if the approximation you're making is too high. And also, ideally, if you just think about a distribution of refraction index, since the speed depends both on elasticity and density, you can think that it's the same implementing this refraction index with a variation of density or with a variation of, we have a fire alarm, actually. I'm sorry.
Don't worry.
I can continue as long as probably it is alarm. Let's see. I mean, I just have a couple of slides. Probably I can continue.
Yeah, sure.
Okay, so I was saying that hope you don't hear the noise, but the idea is if you implement this with the gradient of elastic properties, it turns out to be worse than just having the density. And this is something we realized with this formulation. Then just the couple of slides I'm missing, I wanted just to introduce you this, which is a different type of concealment in some way, which does not refer to cloaking, but just with the idea of having a device that allows you to hear others, but not being heard. So if you are and you can hear it. And this refers to the idea of having null reciprocity that can be implemented with space-time media. And this also refers to the idea of having a modulation that varies in the radial direction. So, so this also refers to the idea of a radial sonic crystal, which is something that was introduced firstly by Daniel Torrent and Jose Sanchez-Teresa, which kind of introduced the requirements you have to apply the block analysis in radial coordinates. Basically, it turns out that you need anisotropy, because when you define the, okay, no alarm. When you define the differential operator in radial coordinates, what happens is you have this, if you want to apply the block theorem, then this operation should be periodic in the radial coordinate. And then if you have 3 degrees of freedom, so bulk modulus and 2 densities, radial and tangential, you can make these terms periodic independently, and then you can apply the block formalism. And so in the end, if you apply the plane wave expansion method, you end up with a dispersion relation for the modes, like the monopole, the dipole, the quadrupole, and stuff like that. And you can open band gaps. So what we thought to do was to introduce a temporal variation also. So for example, here you see the radial density. It not only depends on the spatial coordinates, but also on time, such that the medium is kind of moving, except by it is not moving at all. You just obtain this bias in the reciprocity with a time modulation. And so if you expand this both in space and time, what happens is that you have a quadratic eigenvalue problem that you can use to plot this dispersion relationship for example, for the monopole modes and the dipole modes. And you see, you get these non-reciprocal band gaps. And this idea maybe can allow to design devices for which waves, as I said, can propagate either diverging or converging. In this case, you see the numerical simulation. You have a proper excitation in the middle of the device with the proper symmetry, so kind of monopole or dipole. And you see the wave goes preferably either diverging or converging. So this is it. I apologize for the fire alarm. And okay, I thank you for your attention. And if you have questions, I'm open for them.
Thank you very much, Davide. It was a fantastic talk. So now we would welcome any questions from the audience. Please, people, come forward. I'm sure you have many questions.